So, continuity to the last class or previous class, where we were discussing about the shell momentum balance of the film flowing over an inclined surface, and this application also we had said, say like concentration of say food material in from low concentration to high concentration over the heating surface, and this heating surface also it said can be totally vertical or also can be horizontal, but we have taken an angle beta right with the horizon, that what is the angle beta, and then we have developed the we have assumed something, and then on that assumption we have developed the equations for momentum in and momentum out, both by convective transfer as well as the molecular transfer mode, right. So, let us start then from there, and then since we also said it is the steady state, so the convective momentum that comes out because it is a steady state. So, at the surface both the in and out will become same, and in that case that cancels out. So, only the molecular transport will remain. So, let us look into that. So, then it becomes LW from the previous equation, LW tau xz at the face x minus LW tau xz at the face x plus delta x plus rho g x cos beta into del x L W. So, this is equals to 0, that we come by putting the individual into the governing equation, right. That governing equation we said the rate of momentum in minus rate of momentum out plus sum of the forces acting is equals to rate of momentum accumulation, right. So, we have taken that steady state, so accumulation is not there, and also we have stated that steady state, so momentum in by convection, momentum out by convection becomes identical. So, that also goes out. So, now if we dividing with delta x, L, W both the sides, right, and we make that tau xz at x plus delta x minus tau xz at x over delta x, this is equals to rho g x, because this minus this divided by delta x will make it a differential. So, that is why there is a negative, and this negative on this side will make that both thing on the other side. So, this negative will go to that. So, this remains. So, it is rho gx become positive, and this is also positive. Now, if we put limit delta x tends to 0 from the definition of the derivative, we can tell that tau xz del x of tau xz is equals to rho g x, right, into cos beta, right. Del x of tau x z is equals to rho g x cos beta, right. So, on integrating this, we can say that tau xz that becomes equals to rho gx cos beta into x plus C1, right. Rho gx into cos beta into x plus C1 integration constant. Now, to find out the integration constant, we can now say at boundary condition is at x is equals to 0, tau xz is equals to 0, so that C1 becomes equals to 0. At x is equals to 0, tau xz is 0. Now, you remember we had taken this the horizontal solid board, right, or solid material on which the film was there. We had taken the volume element like that, and we said this was the surface, this was the liquid which is on the solid surface, and this was the open surface which is the liquid gas interface, right. This was the liquid solid interface, this is the liquid gas interface, and we took our coordinate to be here, that this is x, this is y, or this is z, whatever, right. So, we are concerned with this. Then tau xz is like that. So, we can write that in the at x is equals to 0. So, here that tau xz is equals to 0, and that is why it is C1 equals to 0, right. So, we can write then tau xz is equals to rho gx into x cos beta, right, or similarly tau or xz is equals to minus mu d rho del vz del x is equals to rho gx x cos beta, right, or we can write this tau xz is del x of vz. So we can say that del x of vz. So we can say that del vz del x is equals to minus rho gx x cos beta by mu, right. So this on integration we can write vz is equals to minus rho gx cos beta into x square by 2 mu plus C2, right. So if that be true, then we can, say that by putting the boundary conditions, that at x is equals to delta, right, Vz is equals to 0, right. Now, at x is equals to delta means, if you remember, we had said that the thickness of this film is delta. So, we started from here, this is the coordinate point. So, at x is equals to delta, this is the open liquid gas interface, right. So, at x equals to delta, Vz is equals to 0. Why? That was liquid solid interface, and this was liquid solid interface, and this is liquid gas interface. This is liquid solid interface. So our point was liquid gas interface. It is 0th. So delta is this. So del means we have liquid solid interface. So at the liquid solid interface, liquid is clinging to the surface. So Vz becomes equals to 0. So if that be true, we can write C2 is equals to rho gx del square cos beta over 2 mu, right, or Vz is equals to rho gx cos beta into del square minus x square by into mu, right? Or Vz we can write is equals to rho g x into x into rho gx into del square into x cos beta by 2 mu into 1 minus x by del whole square, right? Now V max or V is equals to V max, that can be when x is equals to 0, right? When x is equals to 0. For understanding, this was the open surface, this is the solid surface. We started our x this way, so this is 0, x is equals to 0. This is another, this is the third direction. So in that case, that at x is equals to 0 means this is the open, that is the gas liquid interface. So V becomes V max at x is equals to 0. Therefore, V max can be written as rho g x del square cos beta by 2 mu. So this is the maximum, velocity rho Vx. So average velocity or V average, this can be written as, again we write that between 0 to W, between 0 to del, right, Vz dx dy over integral of 0 to W, 0 to del dx dy, right. This means this is equals to 1 by del, right, 0 to del Vz dx, right. Vz already we have found out, and this can be written as equal to rho g x del square cos beta by 2 mu into 0 to 1 minus x by del whole square d of x by del, right. So that is equals to rho g del x del square cos beta by 3 mu. So average velocity is rho gx del square into cos beta by 3 mu, right. So this is V average. So V max we have seen, V average we have seen. Now the volumetric flow rate. So volumetric flow rate or Q, this can be written as 0 to W, 0 to del Vz into area dx dy. This is equals to W del Vz average, that is equals to rho g W gx, rather W to del square to cos beta over 3 mu, right, over 3 mu. This is the volumetric flow rate, that is either W del Vz average or rho gx W del square cos beta by 3 mu, right. So V average was rho gx del square cos beta by 3 mu. Volumetric flow rate is rho gx W del square cos beta by 3 mu. Then the film thickness delta, this can be found out from the volumetric flow rate or average, whatever with the way we want. So this can be written as 3 mu P Z average over rho Gx cos beta, right? And this also can be written as this was del, right, W del Vz average, and Vz average we had one del, so it will become del cube, not square, right? This becomes del cube. This was one del square, and there is one del from here, 0 to del, right? So in that case 0 to del x, so in that case it becomes like that, del 1 and del square, so del cube. So that is why under cube root of 3 mu q, q is the volumetric flow rate, by rho Gx W cos beta, right? This also can be written in terms of cube root 3 mu m dot over rho square G cos beta, right? So this is the film thickness, right? Then we also look into what is the force, that is Z component of the force, Z component of the force F of the fluid on the surface, or it can be written as Fz is equals to 0 to L 0 to W tau xz at x is equals to del dy dz. This is 0 to L 0 to W minus mu dvz dx at x is equals to del dy dz. This can be written as equals to LW to minus mu into minus rho Gx cos beta into del over mu. So this on simplification can be written rho Gx del L W cos beta, right? Which is, this is known as the Z component of the weight, Z component of the weight of the entire fluid in the film, right? So this is the Z component of the entire film, right? So some more things which we need to know are like this Reynolds number. So Reynolds number for the film flow, we can write Re film, that is equals to 4, that is equals to 4 del V average into rho by mu, 4 del V average rho by mu, right? Instead of dV average rho by mu, that is the pipe flow, dV average by mu, here we can say it is 4 del V average rho by mu, that is the film Reynolds number. Now, for film Reynolds number, there is one good thing, that unlike the pipe flow Reynolds number, where it was 2100 and 2100 and 10 to the 4, that is at the 2100 and 4000 above. So this can be very smaller in terms of film, because film you have different thing which is having low Reynolds number for both laminar and the turbulent. For laminar flow without rippling, now for this, rippling means, what do you understand by rippling? I give a simple example that during your childhood you must have played with this, that you stayed on the bank of maybe river or pond or whatever, right? So say on the bank of the pond, on the side of the pond, you had threw a stone, right? The stone went inside the fluid, there is water, right? After that, there is a wave kind of thing which was generated, right? This kind of situation is known as the rippling, right? This kind of situations are known as rippling. There is no turbulence. There is no turbulence. You have thrown over simple stone, and the stone created a wavy pattern in the fluid, and this you known as the rippling. And this is very useful when it is used in the falling film or similar to that. So this you have to keep in mind, that rippling, without rippling and with rippling means there is a wavy form in the flow, and then that can be said as to be equal to the rippling. So laminar flow without rippling, in that case Reynolds number becomes less than 4 to 25. So laminar flow without rippling is Reynolds number without rippling between 4 to 25. Then laminar flow with rippling that can be between 4 to 25, less than Reynolds number less than 1000 to 2000. It is quite a big number, 1000 to 2000. And turbulent flow can be between or greater than 1000 to 2000, right? So you see that film Reynolds number, film's Reynolds number, your definition or your expression is different than that of the flow through the pipe, right? So subsequently you will also see this is also different when it is flowing through the fluid is flowing through a very small slit, right? The one which we had shown as the two plates through that. Similar to that, if you have a slit, small orifice, small hole, small opening, through that when it is being flown, then it is called that flow through the slit, right? And there you will see that this is not so easy. This is not what I say, not so easy means this is difficult, different than that of the falling film and the flow through the pipe. So Reynolds number expressions are quite different for three types of this kind of flow. One is for the pipe flow, and another is for the film flow, and third is for the flow through the slit. Of course, flow through the slit we have not done, but Reynolds number through the pipe flow we have done, that is dV rho by mu, right? Whereas the Reynolds number through this film we have shown that to be equals to 4 del V average rho by mu, right? 4 del V average rho by mu, and the values are also quite different, and the nature is also different. In this case, we have seen that it has rippling, and we have also said the meaning of the rippling. Rippling is the similar one which you have experienced during your childhood, throwing a stone onto the wave or onto the pond that creates a wave. This kind of wave formation is known as the ripple, right? So, rippling like this, right? So, this is like that, and when it is like this, then we call it to be rippling. So, without rippling between 4 to 25, with rippling it is less than 4 to 25. So, with rippling it is between 4 to 25 and 1000 to 2000, and if it is without rippling, with rippling other than that, the turbulent flow, then it is between 4 to 25 and 1000 to 2000. So, film flow, that is also very important in terms of processing, in terms of heat transfer, in terms of fluid flow, because this is really a commercial aspect which it has wide application. So, falling film we have to also develop very accurately, or this expressions you have to develop, and here we have assumed that this fluid was clinging to the surface, and the free flow or the free end, that is the interface between the gas and liquid or gas and fluid, that was also where the tau was 0, considered to be 0. So, momentum flux was there 0, and we found out the expressions for them, right? So, keep in mind and do this practice with the derivation of the film flow. Thank you.